And this has in particular a very important corollary, is that in particular, if your curve is closed, if gamma is closed, then the circulation of a gradient field is equal to 0. Why? Simply because we saw that if the circulation of a gradient field depended only on the value of, well, the potential at the beginning point and the end point, and if your curve is closed, then beginning and end are the same, and so the values are the same. Okay, so let's illustrate that with our previous example. Okay, so you remember this example was v of xy given by minus y over x2 plus y2 and x over x2 plus y2. We said it comes from a scalar potential, but the domain of this vector field is ortho star. Okay, so domain ortho star. So let's see what we have. We're going to compute the circulation of that vector field on several curves, right? So if it's a conservative vector field and if our curve is in the star domain, then it should be equal to 0. And we're going to see, well, one first example. Let's consider the following curve, okay, gamma, described by you've got, so that would be a part of a circle of radius a, and then you're going to straight line from some value a to b, and then that's a circle of radius b, sorry, and we're going to stop at negative b. Okay, so what do we have? This is in R2 star, of course, I'm not including the 0 anyway, and my curve gamma is describing, well, let's say I'm starting at wherever we want, actually. We're going to go from A to B, then, well, then we go along that outer circle, we reach the point negative B is 0, we go on this straight line, and then we use this inner circle of radius A. Okay? And I want to compute the circulation of V on that curve. Okay, so let's first observe that gamma does not contain 0. Well, in the sense as gamma is a closed curve, and 0 is outside of that. So we could say that gamma is itself included in a star domain because it would be included in, let's say, R2 minus any half line. Let's say that I will say it's included in R2 minus this half line, and that this is included in a star domain. Okay. All right, and if you wonder what the star is, let's say that I could take any, sorry, any point well, what the important is the domain that contains gamma. So I could take any point, and I'm going to reach any other point in that domain from this one. Okay. Anyway, I want to compute the integral on gamma of v. Okay, so what are we going to get? So that should be, I can write this as minus y over x2 plus y2 dx plus x over x2 plus y2 dy. But now we know better. We know how we can describe this curve. Okay, so the first work is going to be description of the curve. Of the curve gamma. Okay. All right. So what do we have? Let's say we go from the point with coordinates a0 to the point of coordinates B0, then we use the half circle of radius B to go to, well, let's say that's point C of coordinates negative B0, then straight line to go to point D with coordinates negative A0, and then half circle of radius A to go back to point A. Okay, so that means that I've got several pieces to my curve. I've got, let's say that this is piece gamma 1, gamma 2, gamma 3, and gamma 4. Okay, I've got these 4 pieces. Straight line, so straight line, half circle, straight line, other half circle. Okay, all right. So, and I can say that gamma 1 union gamma 2, gamma 2 union gamma 3 union gamma 4 is the whole curve gamma, so that I can use something like Schad's theorem. The integral on the line integral on the whole of gamma is going to be the sum of those subintegrals. Okay, now I need to describe them to find parametric descriptions of all these species. So gamma 1 goes from point A0, so that's a straight segment from A0 to B0. So x of t is going to get the value t for t belonging to interval AB, and y of t is just going to be 0 there. Okay, so that's gamma 1. Gamma 2, so that's half circle of radius b, so you know that x of t is going to be b times cosine of t, y of t is going to be b times sinus of t, and we need t to be between 0 and pi, so that I do only half of the circle. Then I've got gamma 3, which is the straight line from the point, so let's see what we have. Okay, gamma 3 is going to be that straight line from the point, so that was A, B, C, from C to D. So x of t is going to take the t value, and t goes from, we have to take care, because we have a sense of circulation, we go from C to D. So t takes the values from negative B to negative A, so that's fine, to negative A. And then y of t is equal to 0. And finally, gamma 4 is just, so gamma 4 is that part. We're using that half circle, but in the anti-trigonometric sense. So x of t, y of t, so this is going to be again a times cosine of t, a times sinus of t, but this time t goes from pi to 0. Okay, so that I use this upper half circle. Okay, t goes from the value pi, decreases to 0. Okay, so the angle value is pi, but it's negative a to a. All right, to go from point D to A. So now I can write my integral. So my integral is going to be, so on each piece, I'm going to have the first component of v times x prime plus second component of v times y prime. Okay, so on gamma 1, I've got, so let's remind us what we had. V was equal to minus y x2 plus y2, and x over x2 plus y2. Okay, so on gamma 1, I'm going to get minus y, but well, let's begin like this. Okay, minus y over x2 plus y2 times x prime. And so we said gamma 1 was just t. Okay, gamma 1, this is this description. right? So on gamma 1, I've got that x prime of t is 1 and y prime of t is 0. Okay, so times 1, which is the x prime of t, dt. Okay, and plus, well, I would have on gamma 1, and gamma 1 was described by, okay, we will have to write this from x2 plus y2 times 0 dt. Okay, so what do we have here? We have actually p x prime q y prime. Okay, now let's be a bit more precise. So we have t goes actually from, so that's let's do it that first piece. T goes from, we said from A to B. Okay, y is actually going to be equal to 0, and x2 plus y2 is actually well equal to t square times dt, all right, plus the integral on gamma 1 of this thing, which would be just t over t square plus 0 times 0 dt. So actually, gamma 1, the integral on gamma 1 is equal to 0. Okay, now let's compute the a second part of this integral, this line integral. So we went from point A to point B. Now let's take the outer circle to go from point B to point C. Okay, so we said that would be described, so this gamma 2 curve would be described by x of t is equal to b cos t, and y of t is b sinus of t, and t goes from 0 to pi. We will need x prime of t, which is minus b sinus of t. We will need y prime of t, which is b cosine of t. So I2, the integral on gamma 2, okay, that's going to be the integral. So we said t goes from 0 to pi. So we get the x component is given by minus y. So minus y is minus b sinus of t divided by x2 plus y2. That's just going to be b square cos square plus b square sine square. So that b square times x prime. So x prime is minus b sinus of t plus the q component, which is x. So x is b cos t divided by x2 plus y2, again that b square, times y prime, and y prime is going to be b cosine of t dt. Okay, so now I can compute this integral. So I get b square sine square of t divided by b square, integral from 0 to pi, plus b square cos square of t divided by b square dt. So in the end, this is really 1, the function 1 on 0 pi, so that's equal to pi, this I2 piece of my curve integral. All right, so let's do the I3 part. I3 part goes from point C to point D. So C has, so we said we would describe this as x of t is equal to t, y of t then is equal to 0, and t goes from negative b to negative a. So I3 is going to be the integral from negative b to negative a of x. So the first component, this is minus y, so this is 0, okay, times x prime of t, which is 1, plus the y component. The y component is x over x2 plus y2, so that would be t over t square times y prime, which is 0. So again, we get that the circulation on the straight line is equal to 0. Okay, and then what do we get? So that's I3, and then we get I4, which is then we're going to go from point D to point A. And we know that x of t is equal to a cos t, y of t is going to be a sinus of t, and t goes from, we said, from pi to 0. That's one thing we have to take care of. We will have x prime of t, which is minus a sinus of t, and y prime of t, which is a cos t. So maybe you can pause and try this by yourself. Okay, so assuming you have gotten some results, so you should get something like the integral. So we said t goes from pi to 0, so I should keep that order for my bounds. And we get, so minus y, so minus a sinus of t divided by x2 plus y2, that's a square, times x prime, so minus a sinus of t, okay, plus the q component of my vector field, which is x. So x is a cos of t divided by x2 plus y2, again that's a square, times y prime, which is a cosine of t dt. And what do we get? That's going to be equal to integral from pi to 0 of, again, we get minus a times minus a, that's plus a square over a square sine square. So we get 1. But if you want to calculate that, pay attention to the fact that the bounds go from pi to 0. So if you want to bounce that back, so that's the same thing as minus the integral from 0 to pi of 1 dt, so that's negative pi. And finally, what do we get? We get that I1 plus I2 plus I3 plus I4 is equal to 0. Okay? 0, pi, 0, negative pi. Is that something we expected? Yes, absolutely. Why? Because this was a conservative vector field on the star domain. Yes, as conservative vector field along a curve included in a star domain. Okay, let's take another example. Well, let's use the same vector field to show you why this assumption is actually important. Okay, let's take another curve. Let's take a simple one, trigonometric circle, and some vector field. All right, so that's the one. It's going to be described by x of t is equal to cosine of t, y of t is equal to the sinus of t. Okay, why is that why can it be problematic? Because this curve is closed and it contains the forbidden value. Okay, that makes it not included in a star domain. So is not included in a star domain for the function. Okay, this is relative to the function. You understand that, right? So not included in the star domain. So let's see what we obtain in that case. So the integral on gamma, and I can add that nice little circle because this is a closed curve of, well, let's minus y x2 plus y2 dx plus x over x2 plus y2 dy then should be given by, so I'm doing the complete circle, so it's the integral from 0 to 2 pi of minus y, that's minus sinus of t, divided by x2 plus y2, that's just going to be 1, times x prime is going to be minus sinus of t. Okay, so that's x prime is minus sinus of t, y prime is cos of t. Okay, so that's the first part plus x, so the q part, x is cos t over x2 plus y2, that's 1 again, times y prime, we said cos t dt. What do we get here? Plus sine square, so the interval between 0 and 2 pi of sine square of t plus cos square of t, which is 1, of course. So I integrate 1 from 0 to 2 pi, that's equal to 2 pi. Okay, why is that shocking? Because it's different from 0. Okay, so I had something that looked like a conservative vector field, but the curve I was integrating it along was not included in the star domain because it contained one of the forbidden values. There was like a hole inside, and then we obtained that the circulation was not 0, even though the curve was closed. Okay, so I understand that's not easy, but then we will practice that during tutorial. Okay, so that's it. Thank you very much.